Okay, so the last mini lecture of this session is about trend filtering. Very briefly, it's going to be a short one. Trend filtering is another way to do non-parametric regression. So we've kind of already seen wavelet approaches. Trend filtering is beautifully simple, and so that's why I want to present it. It also actually works quite well in many cases. So I just want to present this idea because I think it's beautifully simple and also works quite well. So remember, the non-parametric regression problem is we want to fit some smooth mean or spatially structured mean mu to data y. E here is the error term. The basic idea is that mu k minus mu k plus 1 is going to have many elements that are near zero. Okay, so mostly the mean isn't going to change very much. So the idea is that we can fit this model by an L1 penalized regression. And the way to do it is that we're going to use a basis X which is chosen such that XB are the differences, are the changes from one Y to another. So maybe the math is here, but let's just maybe look at, well, yeah, here's the key idea is that beta k in this regression is just going to be the difference in the mean between mu and mu k plus 1. So if we just have a picture, sorry, that's not, yeah, okay. So if, so think of each predictor that we're going to use is, well, the first column of X, but I'm going to write it as a row vector, is like that. And then the next column of X, the next predictor is 1, 1, minus 1, minus 1. So that the idea here, next one, yeah, you get the idea. These are minus 1s here. So the idea here, you can think of this as fitting a basis that looks like this. This is the first, it's a basis of step functions, right? Etc. So the coefficient of this first basis function here is going to be the change in mu between the first location and the second location, right? If I only have a coefficient on that first one, it's going to only have a change in mean between the first position and the second position. Okay, so I guess the coefficient is twice the change, the way I've set these numbers up, but still, you get the idea. We could use zeros and ones. I guess that's another way to do it. Doesn't really matter. The whole point is that you're basically trying to use a basis, a set of basis functions that look like step functions. You're trying to write the mu as a linear combination of these step functions. So the coefficient of this first one is the change in mu at the start, and then this second basis here, sorry, oh dear. This second basis function here that I just erased, that's the coefficient of that is the change at the second position. So if there were only, let's suppose there were only a change at the first position and this second, third, fourth position here, if you had maybe, you could have something that goes along and then up again, something like that. So this basis, if it's sparse in this basis, then you get a piecewise constant mean. So this basis might not be the best basis for every problem, but and in fact there are generalizations of trend filtering which allow slightly higher order, instead of using piecewise constant basis functions, they use piecewise linear, for example. That'd be for first order trend filtering rather than zeroth order. But the key, this is the simplest version, and so the idea here, I guess, is that we can just fit this penalized regression using GLMNet, for example. Actually, there are details of the computation that mean you can do better than just, because X is so special here, you can do quite a bit better computationally than using GLMNet. And there are various, there's a package called GenLasso, which is a generalized lasso that fits this model very, very quickly, exploiting the features of the X. And if you want to see it in action, there's a write-up just here. Sorry. So, okay, so just to summarize, the idea is that you can write the piecewise constant, or the fact that this is sparse can be written as a regression problem, and then you can fit that regression problem inducing sparsity in these changes using off-the-shelf L1 penalties, for example, or you could use an L2 penalty potentially as well. So just to show you how that performs on this example, let's have a look quick. Here we go. It's really, this is the off-the-shelf answer for these particular data, which I think is a pretty good off-the-shelf answer for pushing a line through these points.